I want to use this example to show you when we're working with partial derivatives, we have to be extra careful sometimes. Let's have a look. We have this function, and the goal is to just find the partial with respect to x at 0, 0. So at first you might be wondering, can we just write this into the power function? Look at this as 8x cubed plus y cubed raised to the 1/3 power and do the usual power rule and the chain rule. Sure, let's try that. Bring the power to the front, minus 1. So we get f sub x equals 1/3 8x cubed plus y cubed. 1/3 minus 1, we get negative 2/3. And then use the chain rule, multiply by the derivative on the inside with respect to x. So bring the 3 to the front, so that's 24. And then we have x squared. The derivative of this with respect to x is 0 because it's just y. And then we can clean this up a little bit. So on the top we have 8x squared. Bring that down. Put this as the cube root. And then here we have 8x cubed plus y cubed. And we still have the square. Let me write it like this. Then 0, 0, right? Let's just go ahead and plug in. X is 0, y is 0. When I put 0 in here, the top is 0. When I put 0 and 0 into here and here, and then square that, all that, I still get 0. This is 0 over 0. Have a look. Whenever we're dividing by 0, it has no answer, right? So the answer is just undefined. The derivative doesn't exist. Like however you want to say it, right? It has no answer. But the truth is, no. This right here is not correct. We cannot draw any conclusion with this. And you might be wondering why. This is why I told you guys earlier, when we're doing partial derivatives, we have to be extra careful sometimes. Sometimes we will have to do this with the definition. So let's have a look. So first, let me remind you guys, when we take the partial with respect to x of our function, this right here by definition is the limit as h approaching 0. The partial derivatives idea is just that we are going to keep y constant and then we are going to vary the x. So we will just do f of x plus h here and then the y stays the same, minus the original function and then divided by h, which is very similar to our good old calculus 1 definition of the derivative, right? Cool. Now, we need f sub x 0, 0. So, by definition, this is the limit as h approaching 0. We need f of, here the x is 0, so I will plug in 0 here, and then plus h. And then here the y is 0, and then minus f of 0, 0. And then all over h. Now, f of 0, 0, plugging 0 into here and here, cube root of 0 is just 0, is legitimate. So let me just make a quick note. So that is 0. And then when you plug in 0 into y, that's gone. I just have to plug in h into the x right here. So this becomes the limit as h approaching 0. H in here, we get the cube root of 8h cubed minus 0, which doesn't matter, and then all over h. Now we can simplify this a little bit. This is the limit as h approaching 0. Cube root of 8 is 2, and then cube root of h cubed is just h. And remember to do this inside out. Do not plug in the 0 into here and here and say, that's also 0 over 0. No, don't do that. Cancel out the h first, and then you look at this as the limit as h approaching 0 of just 2. So what's the answer for this? The answer for this is just a 2, right? Very, very nice.